Hello friends, welcome to the series of lectures of Mathematics 1. Myself Hardik Patel from LJ Institute of Engineering and Technology. In the last session, we have seen the basic concept of improper integrals and type 1 and type 2 improper integrals. In today's session, we are going to start with a type 3 and the comparison test in a improper integrals. Now, first of all, what is a type 3 improper integral? It is a definite integral in which one or both limits of integral are infinite and the integrand also becomes infinite. That means the combination of type 1 and the type 2. That means either of limit is infinite and function is also discontinuous in between your interval of integration. Then it is called the type 3. Okay, so the combination of type 1 and type 2 is called type 3. Now this type of integral is going to be evaluated by separating it into the form of type 1 and type 2. Example given, integration from 0 to infinite 1 upon x square dx. Now see, here limit is infinite, that means it is of type 1. Same manner, your function 1 upon x square is not continuous at point 0. Correct? So it is also type 2. That means function is also discontinuous and limit is infinite. That means this is a type 3 improper integral. And if you have a type 3, so we are going to start the evaluation of integration from 0 to infinity 1 upon x square dx. So what we are going to do, we are going to write this integration as this is a function is not defined at a 0 and upper limit is infinite. So this function is going to be this integration is a type 3 integration. So what we are going to do, we are going to write this integration in a two separate integrations that you have to break your integration from any point in between 0 to infinity. So we are going to break it from 1. So first integration is going to be 0 to 1, 1 upon x square dx. Second integration is 1 to infinity, 1 upon x square dx. Now see, here this function is a improper integral of type 1 because limits are finite and function is discontinuous at the point 0. And second, here function is continuous everywhere but the limit is infinite. So this is the improper integral of type 1. So you have to evaluate both separately, and if both are going to be convergent, then the addition is also going to be convergent. That means the original integral is also going to be convergent. Now first we are going to start with a first integral I1. I1 is integration 0 to 1, 1 upon x square dx. Now your function is not defined at 0, so we are going to replace 0 with some constant c1 and limit c1 tends to 0. That will give you integration from c1 to 1, 1 upon x square dx. Correct? Now integration of 1 upon x square, that will be minus 1 upon x. And that will give you, if we are going to substitute the limits, then you will have minus 1 plus 1 upon c1. Now if you are going to put the limit c1, then 1 upon 0 is going to be a infinite, and infinite minus 1 is infinite. So the first integral is going to be a divergent. And since the first integral is divergent, so no need to calculate the second one. Still here we have calculated the second one. Second integration is going to be integration from 1 to infinity 1 upon x square dx, replacing infinity by something c2, integrating it and putting the limits. That will give you the answer 1. That means this part is convergent. I1 is divergent, I2 is convergent. So infinite plus finite, that means infinite. So I1 is going to be original integration is going to be a divergent. Same manner we are going with one another example, integration from 0 to infinity 1 upon x dx. Now see, again this function is not defined at 0 and the limit is infinite. So this is a type 3 improper integral. And once it is type 3, then you have to break your integration from the point in between 0 to infinity. So we are going to break this integration from 1. So you have two integrals. First one is from 0 to 1, 1 upon x dx. Second one is from 1 to infinity, 1 upon x dx. Okay. So we are starting with the first integral. Now in the first integration is limit is from 0 to 1 upon x dx. That means now function is not defined at 0. So we are replacing 0 by t and t tends to 0 plus. Okay. So integration is now reducing in the form of limit t tends to 0 plus integration from t to 1 upon x dx. Now we are going to we are going to integrate 1 upon x, that will be a log mod x, and limit is from t to 1 where limit t tends to 0 plus. Now putting the upper limit and lower limit, that will give you limit t tends to 0 plus ln of 1 minus ln mod t. Now ln 1 is 0 and log 0 is going to be a minus infinite. That means this answer is going to be a infinite. So therefore the integration 0 to 1 upon x dx is divergent. And since it is divergent, so your original integration is also going to be divergent. No need to find the second integral. If it may have convergent or it may divergent, but one of them is divergent, that means the total of both of them is going to be a divergent. That's why the integration 0 to infinity 1 upon x dx is also divergent. Now we are going on to the p integral. See, integration from 1 to infinity 1 upon x raised to p dx is convergent for p greater than 1 and is divergent for p less or equal to 1. Please remember that instead of 1, here if you have any value a greater than or equal to 1, then also the condition is going to be same. Now we are going with a proof. First of all, suppose p is equal to 1, then in that case your integration is going to be reduced in a form of integration from 1 to infinity 1 upon x dx. Now since the upper limit is infinite, so we are replacing it with some constant b and limit b tends to infinity integration from 1 to b 1 upon x dx. 1 upon x as the integration log x, log mod x, or you can write down simple log x as it is greater than 0. So putting the and limits are from 1 to b where b tends to infinity. Putting upper limits and lower limit, that will give you limit b tends to infinity log b minus log 1. Log 1 has a value 0, and if you are going to put the limit to the log b, then you will have the answer infinity. That means for p is equal to 1, your answer is infinite. That means this integral is divergent. Now suppose p is not equal to 1. Okay. So in that case, we have integration from 1 to infinity 1 upon x raised to p dx. So since this limit is infinite, so replacing it with a t and t tends to infinity 1 to t 1 upon x raised to p dx. That will give you the integration x raised to minus p plus 1 upon minus p plus 1, and limit is from 1 to t where t tends to infinity. Okay. Now what we are going to do, we are going to simplify it. That will give you limit t tends to infinity 1 upon 1 minus p, and substituting the upper limit and lower limit, that will give you 1 upon t raised to p minus 1 minus 1. Now we are going to put the condition. Now suppose this power p minus 1, that means p is greater than 1, so p minus 1 is going to be greater than 0. So if this power is greater than 0, then you will have t raised to p minus 1, that means infinity raised to p minus 1. So infinity raised to some positive power, that will be going to be tending to infinite. And 1 upon infinity is going to be a tending to 0. Okay. So in the case of p greater than 1, this term is going to be 0. That will give you minus 1 into 1 upon 1 minus p. That means you have the value 1 upon p minus 1. Okay, if p greater than 1. But suppose if that means it is going to be convergent for p greater than 1. But suppose if p is less than 1, then p minus 1 is negative. Then 1 upon t raised to p minus 1, that will be t raised to 1 minus p. And 1 minus p is positive, so infinity raised to positive is going to be infinite. So in that case, this value is going to be infinite. And infinite into some finite, that will be a infinite. So you will have this integration from is going to be divergent for p less than 1. Correct? So now you have the condition for p greater than 1, your series is convergent, and for p less or equal to 1, your series is divergent. So this is the p integral. Now starting with a direct comparison test. So if fx and gx are two continuous functions for x greater than or equal to a, such that 0 is less or equal to fx is less or equal to gx, and if integration from a to infinity f gx dx is convergent, then your integration fx dx is also convergent. And whatever the value of integration from a to infinity fx dx is going to be less than or equal to integration from a to infinity gx dx. That means if the larger function has a convergent integral, then the smaller function is always going to be a convergent. Secondly, vice versa, if fx and gx are two continuous functions for x greater than or equal to a, such that fx is greater than or equal to gx, and if gx diverges, that means the smaller function is divergent, then the larger function integration fx a to infinity fx dx is going to be divergent. Okay. Now we are going to use the limit comparison test. Suppose fx and gx are two continuous functions for a greater than or equal to x is greater than or equal to a, such that fx is positive and gx is positive. And if the limit fx upon gx has a value L which is in between 0 to infinity, that means it has a value neither 0 nor infinity and finite value in between 0 to infinity, then the integration a to infinity fx dx and the integration a to infinity gx dx both converges or both diverges simultaneously. That means either both are going to be convergent or both are going to be divergent at a time. Okay. Now, test the convergence of improper integral 1 to infinity cos x upon x square dx. Now see, this function is not integrable function and this function is not defined at 0. Now 0 is not in an interval of integration. So this limit is infinite. So this is an improper of type 1. That is the first thing. So this function is improper of type 1. So this is your fx cos x upon x square. We are going to take gx is equal to 1 upon x square, correct? And we are going, as we are aware of, cos x is less than or equal to 1 because maximum value of cos is 1. So what we are going to do is, we are going to write that cos x upon x square is less or equal to 1 upon x square as x is greater than 1, correct? So at the larger integral 1 upon x square, that means 1 to infinity gx dx, which is integration 1 to infinity 1 upon x square dx. So we are going to replace infinity by b and limit b tends to infinity, integration from 1 to b 1 upon x square dx. Now integrate it, that will be minus 1 upon x and limit is from 1 to b. And again put the limit and simplify, that will give you the answer 1. If you are not going to integrate this, then we can directly use the p integral, and as a p integral we are aware of integration from 1 to infinity 1 upon x raised to p. That will be convergent for p greater than 1. Here your p is 2. So it is already going to be convergent. So this integration, the larger integration is convergent. That means larger integration is convergent, then the smaller integration is going to be convergent by direct comparison test. That means integration from 1 to infinity cos x upon x square dx is going to be convergent. Now second example, check the convergence of integration from 4 to infinite 3x plus 5 upon x raised to 4 plus 7 dx. Now see, again this integration is not directly integrable and limit is infinite. So what we are going to do, this is a type 1 improper integral and fx is given by 3x plus 5 upon x raised to 4 plus 7. So we are going to take gx is equal to 1 upon x cube. Why? The maximum power of x in numerator and maximum power of x in denominator, that means x upon x raised to 4, that will give you gx is equal to x cube. Now here we are going to apply the limit form of a comparison test. So we are going to apply limit x tends to infinity fx upon gx. That will be a limit x tends to infinity 3x plus 5 upon x raised to 4 into 1 upon x cube, that will be x cube upon 1. And that will be, if you are going to common out x from numerator and x raised to 4 by denominator, then this x raised to 4 will be cancelled out and you will have limit x tends to infinity 3 plus 5 upon x divided by 1 plus 7 upon x raised to 4. Now apply the limit, that will give 5 upon infinity will be 0, 7 upon infinity will be 0. So you will have answer 3, which is the finite non-zero number, correct? This value is a finite non-zero number. That's why the integration, either both are going to be convergent or both are going to be divergent, correct? But integration from 4 to infinity gx dx, that is 4 to infinity 1 upon x cube dx, that will be written in the form of limit b tends to infinity integration from 4 to b 1 upon x cube dx. And integration is going to be a minus 1 upon 2x square. Limit is from 4 to b. So if you are going to substitute the upper limit and lower limit, then the final answer is going to be 1 upon 32. So this integration is going to be a finite, and that's why this is a convergent. So integration from 4 to infinity gx dx is convergent. That's why your original integration by limit comparison form, integration from 4 to infinity 3x plus 5 upon x raised to 4 plus 7 dx is also going to be convergent by limit comparison test. Okay. Instead of this integration, you can directly also apply the p integral, because see, if instead of 1 to infinity, you can write down from a to infinity where a is greater or equal to 1. Then also the p integral is applicable. Okay. Second example we have taken is test the convergence of integral from 1 to infinity e raised to minus x square dx. Now e raised to minus x square is continuous everywhere, and here limit is infinite. So generally comparison test is only applicable for type 1 improper integrals. Please remember it. So here fx is e raised to minus x square, which is continuous everywhere on interval 1 to infinity. And since we are already aware of x square is greater than or equal to x for every x greater than 1, correct? So if you are going to multiply it with minus, then you will have minus x square is less or equal to minus x. And if you are writing it in a form of exponent, then e raised to minus x square is less or equal to e raised to minus x. Now we are concerned with the integration from 1 to infinity e raised to minus x dx. So this is the improper of kind 1. So replace infinite by t, and t tends to infinity. That will give limit t tends to infinity integration from 1 to t e raised to minus x dx. But e raised to minus x is the integration minus e raised to minus x, and limit is from 0 to t. Substitute the upper limit and lower limit. That will give limit t tends to infinity e raised to minus 1 minus e raised to minus t. See, you have minus e raised to minus t minus minus plus e raised to minus 1. So this term is written first. Now if you are going to apply the limit, so e raised to minus infinity has a value 0. So you will have answer e raised to minus 1, or you can say that it is 1 upon e. Now this is finite non-zero number, correct? So this integration is convergent. So by direct comparison test, the integration from 1 to infinity e raised to minus x square dx is also going to be convergent. Okay, because here fx is less or equal to gx, and integration gx is convergent. That's why integration fx is going to be convergent by direct comparison test. These are the topics which we have covered in today's session. If you have any doubt or any query regarding this topic, then please feel free to contact me. Thank you so much.